Hi everyone, thanks for checking out this video. So this is going to be a lesson about how to calculate Shannon entropy and mutual information in Python. And actually this is one of my little pet peeves about Python, is that I actually haven't been able to find a good like built-in function to do this yet. So a lot of other like statistical measures like correlation and things like that, you can just find like a built-in Python function. But for mutual information, I haven't really been able to find any good like built-in Python function. So whenever I'm working with this, I basically have to like write my own function for it. So I'm making a video to show you guys how to do that and kind of explain these concepts. Okay, so before we get into mutual information, we have to talk about this thing called entropy, or you might also hear it called Shannon entropy, because it's named after the inventor of information theory, Claude Shannon. So basically, entropy is basically like the measure of the uncertainty of a random variable, or you may also hear it called, you might hear it called information, which it seems to be like a contradiction because if it means information, how can it also mean uncertainty? Well, it means information in the sense that it's like it measures how uncertain a random variable is, and it also measures, like, in the same way, how much information you're getting when you find out the value of a random variable. So basically, the more uncertainty there is to a random variable, the more information you're getting when you find out the value of that random variable. I mean, if, like, for example, if there was zero uncertainty, like if the random variable was just a constant number, then you would not be getting any new information when you found out, when you took a draw of that random variable and you found out, like, oh, it's the same thing that it always is because it's just a constant. Whereas if a random variable has a lot of uncertainty, then every time you take a draw of the random variable, you're getting a lot of information about what its value is. So that's just one way to think about it, because at least for me, at first, I found it confusing hearing it called uncertainty and also information, but that's kind of the explanation behind that. So here's the formula for entropy. A lot of times by convention, it's called h of x, where h is like the function for entropy, and then x is a random variable for which we know the probability distribution. Okay, and I know this part looks a bit confusing at first, but I'm going to walk you guys through step by step, and then we'll also do an example, and you guys are going to see it's not actually that confusing. So basically, we have our entropy function h of some random variable x equals negative, and I'll explain why in a second why we're making this whole thing negative. And then basically, it's just a summation where for each possible value of x, we take the probability of that value multiplied by the log base 2 of the probability of that value. And the log base 2 is important here because we want our like our unit for this to be bits. So if you guys know like information theory, like the unit is bits, which is like kind of, you know, like on, off, 0, 1. That's why we're using the base 2. That's, we want the answer to be in bits for the unit. But yeah, so basically the way this function is set up is that when you take the log base 2 of the probability, you're going to be getting a negative number unless the probability is 1. In that case, you're going to be getting 0 here. So basically, it's like we said, if you have no uncertainty at all and you just have some value with the probability of 1 every time, then this whole thing is going to be 0 because you're going to get log base 2 of 1. So this will be 0. And then times 1, 0 times 1, also 0, and then this whole thing just becomes 0. So if you have anything just having a probability of 1, and you're just getting the same value every time, then the entropy, the whole thing will just equal 0. But if you have like different probability distributions where there are actually possibilities of different values, basically the smaller numbers you're getting here, for the probabilities, like the smaller the probabilities are and the more there are of them, you're going to be getting like larger and larger negative numbers out of this log base 2 here. And basically you're going to end up with this whole summation just being like a larger and larger negative number. and then that's why at the end we just make the whole thing negative to just convert it back to like a positive value for the entropy. So you guys might be a little confused at this point. So let's just do an example to kind of solidify this concept. So I'm just going to give like the most basic example ever, just a fair coin flip, just probability 1/2 that you get heads and 1/2 that you get tails. Let's just on the board compute the entropy for this like fair coin flip probability distribution. Okay, so I'll just say we have our random variable x, which is the coin flip, and it's going to be heads with probability 0.5 and tails also with probability 0.5. Okay, so this is our probability distribution for our random variable. It's going to be heads, probability 1/2, tails, probability 1/2. So let's see if we can just go through this entropy formula step by step to compute what the entropy of this fair coin flip will be. Okay. We're going to have negative here, right? Negative. And then I'm just going to do the whole summation like right here, okay? So let's just start, like the first value that x can take is going to be heads, and the probability of that is 0.5. So this first probability here is going to be 0.5. And then that's going to be multiplied by log base 2 of 0.5. So the log base 2 of 0.5 is going to be -1, right? Because it's basically 2 to the -1 equals 0.5, right? If you guys just need a like refresher of how these logs work, yeah. But yeah, it's going to be -1, right? Let me just quickly erase this. Okay, so that covers our first xi there. That was the heads. So we just said 0.5 times log base 2 of 0.5, which is -1, right? And then it's a summation, so we have to do the same thing again for our next value of x, right? So this is tails. It's going to be the same thing as the heads because this is also probability 0.5. So we're just going to have the probability of tails 0.5, and again times -1, because it's also 0.5 for the probability. Okay, so then we have negative, all of this equals -1, right? So -1, so it's just +1, right? So the entropy for this fair coin flip distribution is just 1. Okay, so hopefully you guys are following me at this point. This may also become easier when we do it in code too. So the next thing I'm going to show you guys is that we can also talk about this this concept of entropy for a joint distribution of more than one random variable. Okay, so this is the formula for the joint entropy. Actually, let me even just make this clear. I'll write it up here. Joint entropy. So basically, this is the same concept, except it's for a joint distribution of two random variables. So I call them x and y here. So this is like if we have a joint distribution of these two variables, x and y, where we know the probability of each like combination of them. And yeah, so the way we calculate the joint entropy is basically the same, except we do it in like a pairwise manner, where we look at the probability of every possible pair of values for x and y. Take the probability of observing that pair of values times the log base 2 of that probability of that pair of values. And then we just add them up the same as before, and then make the whole thing negative the same as before. So this is a little bit more complex. So I'm not going to actually do an example on the board for the joint entropy, but it's basically calculated the same way as the single variable entropy, except you just have to look at the probability of each pair of values. And just for the notation here, like I would recommend not getting too wrapped up in the notation, but I just said like I just called the actual values of these random variables lowercase x and lowercase y, and then I just did the summation over all lowercase x's that are elements of the set uppercase x, which is the actual random variable, and the same thing for y. So lowercase y within the set uppercase y. But yeah, don't get too wrapped up in the notation. But yeah, this is just kind of the same idea. I think also this will probably become even clearer and make more sense once we write it in code, because then you guys will be able to see like what's actually happening in the code and how this is actually getting calculated. Okay, so at this point we have everything. We have all the concepts we need to be able to write the mutual information. So mutual information, write it down here. So the mutual information between two random variables. To calculate this, you basically just add together their separate entropies. So I'll say hx plus hy. Remember, these are the separate entropies, the single variable entropies of them, minus the joint entropy. So let's just think about what this means conceptually for a second, okay? So remember, we said that the entropy is like the measure of the uncertainty of a random variable. So if two random variables are not dependent on each other at all, they're not statistically dependent on each other, then the uncertainty of the joint distribution of them will be the same as the uncertainty of the two combined separate distributions of them. So basically, if we have zero mutual information, that basically means that the joint distribution, the joint entropy equals the combined separate entropies, meaning that we still have the same amount of uncertainty in the joint distribution as we had in the two combined separate distributions. But if we have less uncertainty in the joint distribution compared to the two separate distributions, that means we have some amount of mutual information. So basically, if we see that this if this h of x and y, the joint entropy, if this is less than the two combined separate entropies, then we'll have some positive mutual information here. So hopefully you guys will follow me. Yeah, it might take a second to like wrap your head around, but yeah, I just recommend thinking of this in terms of uncertainties, and just again, to kind of repeat myself, if we have less uncertainty in the joint distribution compared to the combined separate distributions, that means we have some mutual information that we're getting between the variables. Okay, so basically this is the explanation of entropy and mutual information, like how to do it by hand if you know what the distributions are. But what I'm going to show you guys in the code is going to be a little bit different. I'm going to show you guys how to calculate the entropy and mutual information if you're just given data and you don't actually know the underlying distribution that's coming from. So you guys might have noticed that for the example I gave like a discrete probability distribution example where there's basically two values it could take and you know the probability for each one. But when you get actual data, it doesn't look that nice. So basically, when you're trying to do this for actual data, you need to empirically estimate a distribution of it, I guess I'll say. So the way we're going to do that in the code is basically if you have some kind of like distribution of data, say it looks like that or something, that's like the underlying continuous distribution of the data. You can empirically estimate a distribution by like binning the data as if it's like a histogram or something. So basically, to calculate all this stuff in the actual code, if you have some kind of continuous data, you need to do some kind of binning process to like discretize the data. You need to come up with some kind of actual like estimated empirical discrete distribution based on a binning strategy like this. So if you guys are confused at this point, just bear with me for a second, and when we get to the actual code, I think it's gonna make more sense. You guys are gonna see that it's not so difficult. But yeah, like so far, everything we've done so far in the video, this was the difficult part already. Just the concepts of this stuff, that's the difficult part. When we get to the code in a second, the code is actually pretty easy. It actually doesn't take very many lines of code to be able to do all this. So yeah, let's get to the actual Python code now. Okay guys, so it's like I said, like what we did on the board already was kind of the hard part, like understanding the concepts of this, that's kind of the hard part already. The actual code isn't really super complicated. So the code's actually, like hopefully this will be kind of the easy part for you guys. But yeah, so let's get started. So first thing we're gonna do is just import two libraries we're gonna be using. We're gonna import the random library and then import numpy as np. And then, so the next thing I'm going to do, just to have something to work with to test out these functions we're going to be writing, I'm going to make up some like fake data that's going to be kind of like the coin flip data we were talking about, just so we can test on it and make sure our functions are working properly. So I'm going to define this random variable x, and then I'm going to say for I in range 1,000. I'm going to say lowercase x draw equals random dot rand int 0 to 1, and then x dot append x draw, and then let's just print this out to make sure it's working okay. Yeah, so that basically gives us like a coin flip type example where it's just like 0.5 probability of having 0 and 0.5 probability of having 1. And then we can just use this like fake data set to test out some of these functions that we're going to be writing. Okay, so let's just start first of all with the regular entropy function. So I'm going to say def entropy. I'm going to be passing in some random variable. I'll just call it x for here. And then bins is going to be the number of bins we're using to empirically estimate our empirical distribution. Okay, so the first line here is going to be bin distribution equals np dot histogram, the name of our list of our random variable, and then bins, and then this is going to give us like a array type output, and we want the first element of that array, so index 0. So yeah, this is a bit of a confusing line, but let me just show you guys what this is actually printing out. Yeah, okay, so let's just try this out here. So we're going to say passing in our random variable x that we're filling up with these like random coin flips, and then 2 bins. Let's just say 2 bins. So let's just see what this gives us. Yeah, so basically this just like bins the data and then reports the number of observations in each bin. So here it's like, and let me show you guys what it is too if we just remove this this first element. So yeah, if we remove that index 0, it also gives us like the boundaries of the bins. So this is basically saying there's 1 bin of observations between 0 and 0.5, and we have 507 of those observations. And then there's another bin with boundaries on 0.5 to 1, and we have 493 observations in that bin. So basically we've empirically estimated a distribution based on this binning strategy. And I know here it's a discrete data set anyway because it's only zeros and ones, but the reason we're doing this binning is that this kind of binning could still give us a probability distribution even for a continuous variable. So I'm going to show you guys towards the end, we're going to use a continuous variable data set and then still use this binning strategy and still be able to calculate these things. But yeah, so this is all this line is doing here, and then we basically add in this index 0 line here so that we can just get the numbers, like an array with the numbers of observations in each bin. Okay, so what we have to do after that is we need to convert these numbers of observations into actual probabilities. So the way we're going to do that is just say probs equals binned dist divided by np.sum of the binned dist. So basically, yeah, let's just also print out what this is. Yeah, so basically all this line does is it divides both of the bins by the total. So it basically just converts these into probabilities. So yeah, it's just just dividing both of these observed numbers of observations in these bins. We're just dividing that by the total number of observations to get these into like the actual probabilities. Okay. So then the next thing we need to do is we need to get rid of any bins that didn't have any observations, just because we don't need those for the calculation. And in fact, if we do include them, it'll actually, if we have a bin with probability 0, that will actually screw up the actual calculation, because you can't take a log of 0 or else you get this undefined value error. You know what I mean? It'll just give an error if you try to do that. So yeah, we need to get rid of any bins with probability 0. So basically we're going to do that by saying probs equals probs brackets np dot non-zero probs. So yeah, it looks like kind of like a fancy seeming line here. But basically, this is just a line that we're adding in case there was some bin that had 0 observations. We need to get rid of that bin so that we don't have any bins that have probability 0 in them, because that will screw up our calculation when we try to take the log of it. But yeah, that doesn't really apply for this example. But it's just putting that line in. It's like a line to keep it safe in case we did pass in a random variable, and then we did end up with a bin having probability 0. We want to get rid of that, basically. And then the last line here is to actually calculate the entropy. So basically we're going to say entropy equals negative, remember the whole thing's negative, np dot sum, because it's a summation, we're summing up the whole thing. It's just, and then just the sum of each probability times the log base 2 np dot log 2 of that probability. And this is basically going to sum them up in like an element wise sorry, I mean this is going to like multiply them in an element wise fashion, and then sum up all those products, and then just make the whole thing negative. So let's just make sure it's working. Let's just print out the entropy here. Try this out again. Yeah, looks like it's working. Looks like it's, if you guys remember on the board, we calculated like by hand that if you have the fair coin flip, you get an entropy of 1. Looks like we're getting about that, so it looks like it's working properly. And then the last thing to do here is just return it. This is a function we're going to be using, so we want to just return this entropy value. And then maybe I'll get rid of these print lines here. Okay. Yeah, so we're good now for the entropy of a single variable. So now the next thing to do is we need to do the joint entropy. Actually, you know what? For this part, I'm actually going to be a little bit lazy and just copy and paste in this function, because it's so similar to this first function that we wrote. I'll just actually copy and paste in this one, being a little bit lazy. And yeah, I have some comments on this one too, explaining what's going on. But yeah, basically we're doing almost the exact same thing as in the single variable entropy, except this time we have 2 random variables. They're being passed in as lists. So we have 2 random variables, x and y, and then we use a slightly different we use a slightly different NumPy function to calculate the joint histogram. Oh, this actually, yeah, we don't actually even need this. I don't know why I had that actually. But yeah, the only other difference is that we're using a slightly different histogram function here. In the single variable one, we used np.histogram, and in the joint one, we're using np.histogram2d. And then, yes, slightly different syntax here, but basically we're getting the same thing. We're just getting like the binned distribution, and then we're dividing the binned observations by the total to get it into like probability format. Then we get rid of any zero probability bins, and then we just calculate it up using actually like basically the same exact line as before, and then we return it. So yeah, sorry for being a little bit lazy there, but I just figured, yeah, the joint entropy, the function is written almost exactly the same way as the single variable entropy, except we're just passing in two lists of observations for two random variables, and then using a slightly different NumPy function to calculate the histogram. But yeah, just to be safe, let's just test this out. So I'm gonna also just make another variable y here, and then I'll just do the same thing. Let's say y draw, and then y append y draw, and then let's just see what we get for the joint entropy of x and y. Okay, yeah, looks like it seems to be working okay. You guys might notice we got about 2 because each of these separately have an entropy of about 1, and then since they're independent random variables, I wrote them this way on purpose. They're just independent coin flips. They don't depend on each other in probabilistic terms. So the joint entropy is just the sum of their individual entropes because they don't have any mutual information between them, really. So yeah, the separate entropies are about 1, and then the joint entropy is just the sum of those, which is about 2. But yeah, looks like up to this point things are working okay. So the next thing we're going to do is actually write a function for our mutual information. So I'm going to say def mutual info, taking in a random variable x, random variable y. These are both going to be passed in as lists of observations for these random variables, and then the number of bins we want to use. And I've been using 2 bins so far because I wrote the example to deal with coin flips. But if you're dealing with like an actual data set where you don't know really what the underlying distribution is, then you may want to like try out different numbers of bins and kind of see what kind of answer you get for like different numbers of bins and like different binning strategies. But yeah, it doesn't have to be 2. It could be really any number greater than or equal to 2, because it can't really be 1 because then that'll be meaningless, you know. But but yeah, any number 2 or greater could be the number of bins. But yeah, okay, so def mutual info, taking in x, y, and the number of bins. So basically, we're just going to calculate the mutual information in terms of the entropies. So we're going to say h x equals entropy x, and then the number of bins. So we're just calculating the individual entropy of x. Then we calculate the individual entropy of y, again with the same number of bins. And then the joint entropy, h, called hxy, equals joint entropy x, y, and the number of bins. By the way, I'm just making the simplification here that we're using the same number of bins for both the x and y distributions. It doesn't have to be that way. You could use different numbers of bins for each one. But yeah, that's a bit more advanced. You can just write the code a bit more advanced to do it like that. For the purpose of this video, I'm just assuming that however many bins we're using for one, we're also using for the other and for the joint distribution. Although I should say for the number of bins for the joint distribution, it's it's like the number of bins squared, because it's like the number of bins for each one. So the number of bins we're doing for the joint distribution is really 4, because it's like 2 by 2. It's like 2 x bins and 2 y bins. So it's like 4 bins really for the joint distribution. But yeah, I'm just assuming for now that we're not using different binning strategies for the two different variables. Okay, and then once we have these, we just say mutual information equals hx plus hy, minus h xy. Yeah, just same thing we wrote on the board, and then we're going to return the mutual information. And that's really all there is to it. Yeah, it's really pretty simple, not much else to do. So for the rest of this video, I'm just going to show you guys a couple more examples, just like proving to ourselves that this code actually works. So I'm just going to move this down here again, keep using these examples. Yes, let's just try this out. Let's just try out what we get for this. So I'm going to say print mutual information of x and y. Let's try it out with 2 bins. And yeah, remember these are independent coin flips. They don't depend on each other. So let's just try this out, see what we get. Yeah, so we get a very small number, about 0, because I did write them in a way that they are independent of each other. Yeah, so it looks like, at least for this, it's working properly. It should work for different numbers of bins too. Like, let's just try it out. Even though I know that it's supposed to be 2 bins, because I wrote it like a coin flip. But let's just say that we wanted to use 10 bins. If we do it like this, we should be getting a lot of bins with 0 observations. But remember, we're eliminating those bins that have probability of 0, so it should still work if we wrote it properly. So let's just try it out with 10 bins and see if it works. And yes, it still works. We still get a very low number, about 0. Now let's try something else. Let's just say, let's just make it so that they do depend on each other. So let's just say that if we get a 0 for x, yeah, say if x draw equals 0, then we randomly choose y. But else, so basically if x draw equals 1, if we get a 1 for x, then we're going to say y draw equals x draw. So yeah, like here I'm basically introducing a little bit of dependency. So now y actually does depend on x, because yeah, if we get a 0 for x, then we pick y randomly. But if we get a 1 for x, then we set y equal to x. So let's just try out this and see if it works. Yeah, can keep 10 bins for now. Should work either way. Yeah, so now we don't get 0. Now we get 0.33 about. Oh, by the way, guys, this measure of mutual information it does not have an upper bound on 1. You can get values that are greater than 1 for mutual information. Yeah, so it's not like Pearson correlation where it's between like -1, 1 or something. It's actually like the lower bound is 0, and it can go higher than 1. It does not have an upper bound on 1. Okay, so yeah, it's a couple examples. Next, let's try out a continuous distribution example. So for this, I'm going to copy and paste in something. Yeah, I'm going to comment out this for a second. And yeah, let's just try continuous distribution example drawn from normal distributions. So let's say that we have x, where instead of being a coin flip, it's a random number from a normal distribution. So I'll show you guys for a second like what we get with these. Let's say so this function basically just gives draws from a normal distribution with a mean of 0 and a standard deviation of 100. Okay. Yeah, mean of 0, because it's 0 by default if we don't specify, and then scale is the standard deviation. Just set that to be 100. Whoops. And then so we'll use that for our X draw, and then we'll say the Y draw is a draw from a standard deviation. A draw from a normal distribution where the mean is whatever we got for the X draw, and then the standard deviation, if we leave it undefined, then it'll be 1 by default. So yeah, so X is a draw from a normal distribution, mean of 0, standard deviation of 100, and then Y is a draw from random distribution from a normal distribution, where the mean is whatever we got for the X draw. So yeah, this is now a continuous distribution. They're continuous variables, but because we're doing this binning strategy, we should be able to properly discretize these distributions and get empirical discrete histogram type distributions out of them. Okay, so let's just see what we get for this. And yeah, so we do get some mutual information between them about 2.5. Yeah, like I said, it can be greater than 1, so we're getting like 2.5 here. Yeah, but just for one more example, let's just see what happens if we make it another normal distribution not dependent on X though. So we'll just make it normal distribution not dependent on X. Then yeah, it's back to I mean, it really should be. We're getting a little bit more than 0 here, just because you know, it's like an empirical random data set. You can get a little bit more than 0 just by chance. But if we make this like a lot of draws, then it's gonna eventually get pretty close to just being 0. Whoops, sorry. Yeah, that was taking too long. I'll give it a lot of draws, but not that many. Maybe a little bit more, but. Sorry, this is taking too long. But yeah, if really the theoretical mutual information between these two here is 0, but since we're dealing with a real random data set, you can get a little bit more than 0 just by chance. But yes, as we do more and more draws, it's going to get basically closer and closer to 0 here. Okay, so that's all I have for you guys for this video. Hopefully everything's making sense. Like usual, I'll just put the code up on my GitHub if you guys want to download it and try it yourself. But yeah, any questions or anything, just let me know in the comments. I'll try to answer them. And yeah, thanks for watching, and see you guys next time.